One of the most prevalent problems in cryptography today is exchanging the keys between two communicating devices. We don't just want to establish a common key, but we want to do so in such a way that anyone who's listening to the communication between the devices do not find out the key. Let's take a look at the problem. Alice and Bob wish to exchange the keys before they begin communicating. The problem, as you might have noticed, is Darth, the bad guy, is listening to their communication and intercepts the key being sent. And if Darth gets the key, then encrypting the data using that key is basically pointless. How do we solve it then? One of the earliest solutions to the key exchange problem was Diffie-Hellman key exchange, which was proposed by Whitfield Diffie and Martin E. Hellman in 1976. Here is how it works. To simplify the solution, we shall see how we can agree upon a common color first, without Darth knowing the common color. Alright? Alice and Bob agree upon an initial color publicly, say yellow. Since Darth is listening to the conversation, he also knows this color. Now, Alice randomly selects a private color, in this case red, and Bob does the same. He selects blue. Now Alice uses the two colors she has and combines them to produce a third color, orange. Bob goes ahead and does the same thing. He combines the public color yellow to his private color blue to get the third color, green. Alice then sends the color she generated to Bob. Realize that Darth is listening to the conversation and hence knows the color. Next, Bob also sends the color he generated to Alice. Darth intercepts it, of course. The color exchange is now complete. To get the common shared color, Alice uses the color that Bob sent him and mixes it with her private color. She gets the final color. At Bob's end, he takes his private color, blue, and the color that Alice sent him, orange, and mixes them to get the same shared color, brown. So finally, Alice and Bob get the same color without Darth knowing it. Darth cannot get the common shared color unless he has access to the private color of either Alice or Bob. So far, we were able to agree upon a common color securely. But cryptography needs number, not colors. We use a mathematical property of discrete logarithm to exchange the numeric keys securely. Suppose we were given with a problem to find 3 raised to power 2 mod 17. We can easily find out that it is congruent to 9. But if we were presented with something like this, it is really difficult to find the power which 3 needs to be raised to produce 9. These are small numbers. With numbers as large as 512 bits or 1024 bits, this problem becomes computationally unsolvable. So we have a function which is easy to solve in one direction but extremely difficult in the other. Let's use this concept for securely exchanging the keys. As always, we have Alice, Bob, and a bad guy, Darth, who is also listening to the communication. Initially, Alice and Bob agree upon a prime modulus 17 and a generator 3 publicly. Since this is done publicly, Darth knows this too. Next, Alice randomly selects a private number, say 15, and calculates 3 raised to power 15, which is our secret number of course, and takes mod 17. The calculation produces 6. Alice sends this number to Bob. Now Bob does the same thing, takes a random private number, say 13, and calculates 3 raised to power 13, his secret number, and sends and takes mod 17. The calculation produces 12. 12 is now sent to Alice. Finally, Alice takes the numbers he receives and raises it to the power 15, her private number, and takes mod 17, which gives out the final answer 10. Bob, on the other hand, takes the number 6 he received and raises it to 13, his secret number, and takes the mod of 17. The calculation produces 10. So you can see that Alice and Bob reach at the same number 10. Now they can use it to securely communicate with each other while Darth is busy solving the discrete logarithm problem.